the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. At the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Having been here for at least maybe 5 to 7, I don't remember exactly, but I think around 5, 6 seminars here, I know that my talk is slightly different than what you have seen here, because most of the previous talks are like more engineering oriented and of course practical, detailed. Mine is different. I'm an economist. I used to work on global energy systems, so I like this more macro view. And so today I'm going to present you my view. This is a question that I started for myself, the research that I'm doing on global water trade. The question was, what's happening to water crisis at the global level? And this question also probably is not the first order question for an institute in the northeast of US, because in the US, the kind of questions I'm talking about are not first order policy questions. In the US, the water problem, especially in areas like here, is water quality. This talk is more focused on water quantity. That's more of an international development view, but there are also interactions with the topics that have been presented here, and I'm so glad that I'm honored that Dean is also here, Professor. You're formalizing the collaboration between sustainability management and business school. All right, so what I'm going to talk today is, first I will give you a quantitative overview of global water crisis, what are the drivers and what are the trends. Then I will switch to what are the solutions in hand and why we need a food, energy, water nexus. The narration that I will follow in this talk is that I'm convinced the global water crisis is going to be very severe. And then when you look at individual solutions, many of them having been discussed even in this forum, none of them is capable, that's my main message, none of them is capable to address in a scale that's sufficient for that global crisis. Even putting together, still we see that there is a gap. So that's why I call it, we need innovative solutions. Otherwise, we are going to face an over-increasing global gap between the need for fresh water and the availability of fresh water. And then I will end with the knowledge gaps in modeling and analysis, which could be topics of interest for students who want to do thesis. So let me start first giving you an order of magnitude understanding of when we're talking about global water crisis, what do we mean? So here, I looked at the global water footprint. That's the amount of water that all 7.5 billion citizens of Earth are consuming per year. So the unit is giga cubic meter per year. And then you see I have put 4 different uses. The reason that I wanted to highlight this, as I said, if you ask someone in Northeast US, for them, the issue of water is rivers, urban water for power production, quality, etc. Whereas if you look from a global perspective, the quantity of water needed for production of crops is in the order of 8,000. I'm just dropping the units. The quantity used for pasture and production of meat is in the order of 1,000. So altogether, that's 9,000 units of water. If you look at industrial and domestic use, so all sanitation, urban use, etc., this is just a fraction of that. So you have 9 units here, and you have 0.7 units there. So order of magnitude bigger here. Most of the water engineering discussions are around, saving water here and there, trying to take less shower, etc. When you quantify those effects, of course, at the local level, they matter. If you are concerned with, bringing water to a ton, you have to deal with those issues. But when you're looking from a global perspective, from a global budget perspective, saying, I want to aggregate whatever water I have and whatever water I need, those solutions are going to be tiny, tiny solutions. They are epsilons compared to the other larger gaps that we have. That's the story I'm going to focus and open up today. So my major focus will be around these two themes. So from my perspective, global water crisis is a crisis of food at the end of the day. Okay, does global communities see this as a risk? So I used this very recent report by World Economic Forum. What they do, they collect experts every year. They ask, what do you see in front of global community as major risks? I looked at the short-term one. There's not much related to water. We have other stuff, wars going on and so on. When you look at for the next 10 years, global water crisis is number one issue ahead of the global community. And if you look at the other, they are also closely related to water. Climate change mitigation, which is a cause and also being driven by water crisis, extreme weather events, food crisis, which is a direct result of water crisis, and then social instability is partly being driven by drought and poverty resulting by water shortage. Okay, so so it's getting a global critical issue, but it's not yet there. So if you want to be forward-looking and think about problems of next 10 years, it's time to start thinking about those issues. So now let's make it a bit more specific. What do we mean by global water crisis? Let's get some numbers. I'm going to show you a lot of numbers in this talk. So I did a bit of calculations. I looked at the global availability of fresh water resources. You know better than me. The fresh water is only 3% of available water globally. So we have plenty of water, but only 3% of it is usable for agriculture, drinking, etc. That 3%, we define a measure in water resource management, the renewable fresh water per year. That's the amount you get every year so you can use it and get refreshed. If you divide it by global population, it's 6,000 cubic meters. The global average use is around 1.5 to 2. So it's still 4 times larger than what on average we need. So from one perspective, you would say we have 4 times more water than what the average citizen needs, so we have no global water problem. However, the difference between water and other commodities like oil is that water is not a is a point use resource. What do I mean by that is that I don't care where oil is coming from. You can get oil from Middle East, ship it wherever you want, as long as you have enough oil in Middle East to support consuming countries, we are fine. Water is not like that because water has a very high transportation cost. So what matters for me is the special match between availability of water resources, population, and arable land. Because at the end of the day, I want to convert this water into crop. That's what I'm looking from a systems perspective. So what we see is that one issue we have is the spatial mismatch. You have plenty of water in places that you do not or you cannot use. You have plenty of water in the northern part of Canada. You have plenty of water in the center of Amazon. But this is not the water that you can use for agricultural food production. So we need a better measure, which is like effective water, normalized by arable land. Then this number drops a lot. That's one issue, and I will talk more about that. Next slides. And also, that 3% itself is going down by all the factors of climate change, etc. Climate change, one of the effects of climate change is that it's going to contribute to the spatial mismatch. It's going to bring the timing of rainfall and the place of rainfall at times and locations that it's not desirable for us. Okay, this is the third hypothesis. I'm talking about mismatch. Mismatch is between water resources and arable land, and is between population and water resources, because we need water where people are living. If global population was smart and was concentrated on areas where there's plenty of water, at least part of the problem would have been resolved. To understand that, in this graph, I'm putting the per capita availability of water, and I'm putting the total fresh water available for each country. If people were migrating freely so that they leave countries without water towards countries with water, this line should have been vertical. meaning that independent of your total availability, people should move in a way that per capita availability should be equal across different countries. They should be levelized. What we see in reality is not like that. So you see a big dispersion in the per capita endowment because a lot of people may live in a country with low water availability. This is the thing, the point I started my talk with, that if you look from the perspective of different continents, the criticality of water for food would be different. So if you look from a European perspective, in Europe only 21% of water goes to agriculture. For Europe, the biggest crisis of water would be in the industrial sector and power sector, etc. If you look at US has of course bigger agriculture, but still it would be half-half. If you look from an African or Asian country's perspective, the biggest chunk of water being used in agriculture. So that's why taking a Eurocentric, American-centric view to water problems would be very different than if you take a global one or an African one. Okay, now let's go talk about trends. So that's like static view, trying to justify that there is a crisis. Now let's see what's going to happen in the next couple of decades. Is it going to get better or it's going to get worse? So among a lot of data that I put out here, I tried to separate a few major first-order trends. First trend is the population prospect. So at the end of the day, I'm concerned with per capita water availability. Think of that, forget about for the moment the climate change. My inflow of water is more or less constant. Think of this. However, the denominator, which is the population, is going to increase over time. The more population, the less per capita water. So what are the trends? We are more or less here, 7.5. There are lots of scenarios, but the most likely scenario is that the population will grow until the end of the current century to like 11 billion, and then you would have a decline in the fertility rate and a decline in the population. Countries' economic growth will slow down the fertility rate and population growth, but when we put together all the countries and model the economic growth, still the ongoing path is that we're going to make the population in the order of 50% more current compared to current form. So we'll have one pressure point from there, one order of magnitude there. Then the question would be, what's happening in the distribution of water across different countries? So for this purpose, I took the per capita water for different countries over the past 5 decades. I said, okay, now let me look at the distribution across different countries. See if the distribution of water is getting more equal or it's getting even worse and more unequal. So the first one is just the global per capita. You see we went down from per capita 13,000 cubic meters to what I showed at the beginning to around 6,000. So it's already went down to half. Then I calculated 3 statistical measures of dispersion. The first one is the coefficient of variation. So what I did, I looked at cross-sectional variance on each year divided by the mean to see whether dispersion across different countries is getting worse or better. You see that the coefficient of variation across different countries at each given time is getting worse. Then I calculated the Gini coefficient, which is the standard measure of inequality in the distribution. Again, it's getting worse. And also an interesting factor, the skewness, which shows me, do I have countries who are getting, or in the extreme? Again, the skewness matrix is also getting worse. So the second message we get is that per capita water is becoming less and less, and also inequality in access to water across different countries is becoming worse. Second factor. The third factor, which has a smaller quantitative effect but still is a factor, is the trend of urbanization. We know that when people move from village to urban areas, the footprint of energy and water consumption goes up from the lifestyle change. So that's another one. That's smaller compared to the other one, but we have a bigger one coming up. That's the effect of diet. So that's something, I have a couple of papers on water footprint and virtual water there. People are sick of hearing this all the time from the researchers, but let me show you some tables. This is the water footprint for producing 1 unit of viscose. For instance, for producing 1 kilo of beef, 2 pounds, here is US, I have to talk about pounds, you need to use 13,000 liters of water for 2 pounds of beef. For a cup of coffee, you have to consume 200 liters of water to get 1 cup of coffee. Right? So And then pork is better in that respect. You go down, for wheat it's around, depending on the country, between 1,000 and 2,000 liters of water, 2 cubic meter. So what you see is that when you look at a meat-based diet, the water footprint is almost 10 times larger than a vegetarian-based diet, which is something known in evolutionary biology very well, right? We know that in order to raise a cattle and get 1 kilo of meat, you have to feed them 10 times bigger, so the water footprint more or less increases by order of magnitudes. And you can have, this table exists for each individual product you want, so I have some papers on that. Okay, so why do we care for? Okay, what happens is that we have around 2 billion to 2 to 3 billion members of global community whose diet is closer to a vegetarian diet. But they are subject to economic development. They are getting richer and richer, in countries like China, India, and you can quantify the effect. People have done on that. So they are moving from this layer of hierarchy of food consumption to this layer. So the water footprint of consumption is significantly increasing. Economic development is a great thing. Part of the meaning of economic development is that you get more sophisticated, nicer diets, which includes things like chocolate, coffee, meat, sugar. These are all very water-intensive crops, basically. So that's something the European Union has started a campaign encouraging its own citizens to sort of cut back and go back to a more modest, less meat-based diet. So to quantify, a typical vegetarian diet per day per person would have a water footprint around 2.5 cubic meters. If you are a typical meat-based diet consumer, like what we do here, it's 4.2. So you see you have another factor of more than 50% increase when you switch that. Now think of 2 billion people switching from this diet to this one. That would be another order of magnitude effect, basically. Comparable with the whole population growth. Another trend we see is also the intra-year water distribution is becoming worse. So you need water to, in order to have water for agriculture, you should get water in the right time. You don't want to get, in a high rainy season, plenty of water and then having drought for the rest of the year. That's what we are seeing in countries like Bangladesh, India, and so on. So that requires a lot of engineering solutions for intra-year water storage and transform. That's your domain. I'm just bringing it as a global factor of risk. Now something good here. As an economist, I was interested, I'm always asking about the cost of producing everything. Those who have seen me here in the seminars, your speakers talk about something which looks very nice. I always ask, okay, is it cost competitive with other solutions? So here I looked at cost competitiveness of different solutions for water in a simplified picture. This is the cost of traditional water supply, just digging a well and getting water, bringing it from river. You see that over time, the cost of traditional supply is going up, which is not surprising because you deplete, more easy access wells, you need to go to deeper wells, etc. So it's becoming more expensive to rely on conventional methods. However, unconventional methods, two examples would be using desalination units and also recycling, which we had a talk, at least I remember one here, maybe we also had one on here. Their cost is dropping thanks to multiple factors. The technology of membrane is getting better. We know how to, I was talking to Julia about getting algae out of the wastewater, making it usable, etc. So overall, we are at the point that for countries who have high cost of producing water, now these three sources are more or less compatible with each other in terms of unit cost of production. The problem is that there are lots of environmental issues around this. Yeah, that's your area. That's a sustainability question. And also we have a little bit of quantity limitations about these solutions. The water reuse can only be used as much as you can add it. You can get it from the wastewater from agriculture and industry. That's a fraction of total water use. So you cannot recycle everything, but still it can contribute a bit. Desalination only works in areas that you have plenty of cheap energy, seawater, etc. But still it could be one factor. So that's one good news in this global trends. And something that's part of my research, I spend a lot of time trying to figure out this. So you may tell me, yes, water is getting less and less available, but agriculture productivity is increasing. We know that we had the green revolution over the past decades. So if I can have increased productivity of crops, a combination of fertilizers, better technologies, etc., maybe I can overcome that. Maybe I can use the same unit of water, get more output from crops, partly true. But then when we look at the trends, it's a very engineering question. Yes, I have an increasing trend, but that's actually a sign of concern. The sign of concern is that the trend in the increased productivity or yield of crop is linear. The trend in the population growth and diet growth, etc., is exponential. So that's why it contributes to the gap. Basically, there is a limit for increase in the yield of agriculture. I'm not including new things like GMO here. It's more of an aggregate portfolio of different crops. But that's where we are falling behind, basically. And on top of that, another economic factor is, I wish I had this, I should have added this graph here, I had it somewhere. So if you look at the distribution of fresh water, you know that there's a high correlation between availability of fresh water and GDP per capita. You don't have I don't remember any advanced economy which is a water short country, Most of them are highly water abundant countries. Look at Europe, US, Japan, all of them. So a lot of freshwater resources are concentrated in advanced economies. Good, because they are subject to productivity growth, but at the same time, when an economy grows, what happens? Multiple things happen in this, and we see it in the data, is that the wages in these economies start going up. Now the wages go up in Japan, you can work in an electronic factory, or you can work on a rice field. Which one would you go? You probably would go to the electronic sectors. So because of the dynamics of wages and costs, the agriculture sector in these economies are shrinking. One factor. Second, these countries are rich. We know the environmental cause-net curve, saying that when a country becomes richer, it can care more about the environment. So they care more about the environment. They try to, preserve land and, even get some agricultural land back into forest, preserve water resources, etc. So these two factors contribute in overall shrinkage of agriculture sector size in advanced economy. You may say that they're growing over time, of course, but not as much as they would have grown in a counterfactual scenario without these limiting factors. So then they are going to contribute to what I call the skewed distribution of fresh water and arable land, the story that I said at the beginning of the talk. You have a lot of water in places that you cannot turn them into food. And we have a paper with a colleague in the department. We show there that you get I wish I had it here. You get two clusters of countries. You have countries who become richer and they have plenty of water. They become water importers over time. Although they have water, because of these factors, basically we show that they keep their own water resources for environmental use and they import water from less water abundant countries. And then you have other countries who are less developed, and then once they have more water, they export more water. But at the end of the day, you get this mismatch between availability of water and lands intensified by the process of global economy. Okay, so far I showed you scenarios to convince you that the global water crisis, which as I said to me is equivalent to global food crisis, is a serious issue. And for myself, I sum up them by saying, okay, there is an economic factor behind that, rate of economic growth and change in diet, etc. There is a trend coming from technology, there's a trend coming from lifestyle, and there's a trend coming from trend. So that's more or less summation of the factors. Should I stop here? Maybe we get some questions. I don't want to be
Still time.
Yeah, so we can maybe take some questions in middle. I've passed already the half of my slides, so
Okay.
you won't have any time problem.
So I have a quick question. So what I understood is the amount of water is preserved on the earth. It doesn't vanish. It just goes through the cycle.
Not precise. It may change from fresh water to saline water. That's what we are
But
seeing.
still, we can have access if we...
With a very costly desalination. Oh,
It's just a matter of cost.
It's a matter of cost. At the end of the day, everything is a matter of cost. Yes. I will talk about that in a few slides. That's a very, very good point. Yes. If we ignore costs, we have more than enough water.
And also it is the fact that the distribution of access to water has changed against our favor. So
Right.
it goes. So if we somehow use the technology to redistribute the water as the
That would
amount
be very
of
costly. That part would be
water
very
is
costly.
constant.
Because if they could have transported water, we wouldn't have this problem from the first place, because we would have taken water from Amazon and take it to, I don't know, Chile and Brazil,
So
other
my point
places.
is this problem is basically the problem of the wrong distribution of water.
Yes.
Because the amount
One-
is constant.
The amount, more or less constant, ignoring the part that it's going to oceans rather than landing on right places, but yes, more or less constant. More or less constant. So you have this fresh water, 3%, you have the saline water, 97%, and you have a little bit of leak from fresh water to saline because of climate change effects. You know, you get water evaporated from here, then you don't know where it's going to rain. You know, if it's raining in the Arctic, you know, in the northern part, and it finally melts into oceans, you lose it. It's not coming back to the freshwater cycle. But that's a minor factor. You know, theoretically it's possible, but let's say yes, it's constant. But even if we focus on that 3%, as you said, yes, is not going in our favor. Most of the regions. There are regions who are benefiting from this climate change, you know, some Scandinavian countries, etc. But overall, it's a negative.
Yeah, we have one question online here. Why have cost of traditional water supplies gone up? Is it because of the distribution, or is it because the technologies are too expensive for the emerging nations?
No, the technology has improved over time. But what happens is that since the need for water use has gone up, we have this, you know, the common sense theory in environmental resource economics. You have the order of extraction. Order of extraction means that you always go with the least cost source. Now think of a farmer in India. So if you wanted to get water 30, 40 years ago, you would have used it, you know, a shallow well, which, you know, you dig for 5 meters and you get to the water. But now first of all, you depleted those resources. A lot of countries are now facing the groundwater depletion crisis. So the level of the water table has gone down. But even if you have the same level, you need more wells, but the next well will not get to the water in 5. It may get in 10 meters. And now you're talking about 200, 300. We are talking about all these deep wells. But then when your well becomes deeper, you need more energy to take it out, right? So that's a very natural phenomenon. The technology has become better. But since the use has gone up, and that's something, whenever I teach environmental economics, I always say, forget about all the economy of scale that we teach in the production of electronics. In environmental economics, it's completely the other way. It's the diseconomy of scale, because once you increase scale, because of the physical limitation in the nature, and it's true for everything. It's true for oil, coal, agriculture, and water. Because of the physical laws, you always need to, you know, search for the second alternative, and second alternative by definition is less efficient, so your cost starts going up. It's a very physical thing.
I think in places where there is water scarcity, the use of technology like sprinkler irrigation and drip irrigation can be good resources. Like in my state, I come from Punjab in India, and as you told, like our water table is, you know, going down every like 1 or 3 feet every year, because we are growing rice, and rice is not a native crop to our state.
Right.
So farmers are, you know, growing crop which is not suitable to the region, but it ensures like maximum returns every season. So they are growing wrong crop at the wrong place.
That's another
They're
interesting
pumping a
point.
lot of groundwater from below, and their groundwater is going down.
Right.
And so the one solution could be having a sprinkler or a drip irrigation.
Sure.
That Israel is following that.
Right.
So they are able to utilize the water in a desert.
More efficient way. That's where I'm going to talk about that. The one problem with making water use more efficient is what we call the rebound effect in environmental economics, meaning that you want to preserve water resources. Once you introduce those high efficiency technologies, you reduce the cost of access to water for farmers. And if you reduce the cost of access, what the response would be they would add to the intensity. Now they would deplete faster because the marginal cost is low. And you know, people have studied, there's a recent paper they look at, I think in Kansas, they document this phenomena. Yes, you're right, from a local perspective, these are the solutions trying to reduce the cost. But from a global perspective, they are contributing to faster depletion of groundwater. In this talk, I didn't have time, but if you want to have a fair picture, we have to separate the discussion of surface water from groundwater. They have very different economics. I think your example is one of them.
But you include both when you say it's a closed
Yes,
system.
in the closed system, I'm not looking at all those differences, but a more careful view would look at those differently, and you would get very different pictures. There's a recent paper in Nature in March. They tried to document basically, they show that the depletion happens US, China and India and Pakistan, I guess, also my country Iran is among them. So they show that the majority of depletion is linked to the trade of food. I think it's related to what you're saying. Like, you want to create job for people. You want to create, the local economic development. You introduce high-value crops, which by definition, high-value crops usually are very water-intensive. And by doing that, you create short-term benefits, but then the difference between river water or green water, which is like, the rain-fed pasture versus groundwater, that groundwater is exhaustible resource. Once you use it beyond the recharge point, you're going to deplete it. So they are short-lived resources. And that's exactly part of the global crisis in countries like India, China, and part of the US, California. Okay, good discussion. So now let me sum up the solutions. Now we talked about this basically. We said, okay, you're going to need water in agriculture, industry, and part of it for ecosystem. We know that, the recommendation of UN is that this part should not be more than 40% of global freshwater availability. You want to leave enough water for the ecosystem, not to disturb ecosystem. So you can't take all that 6,000 that I was talking. Even if you had it, you're constrained by only taking maximum 40% of it and leave it the rest for the nature. And the availability of water, freshwater resources, you see a gap. The question is how to fill this gap. So, people thought about this gap and this new term, water, energy, food nexus, which is a very, very hot topic. NSF has a program on that, and you see it just emerged over the past 5-6 years, but now it's becoming very, very important, interdisciplinary, interesting area. They realized that you cannot think about water crisis without thinking about energy crisis and food crisis, so that you have to put them together in one framework. And if you're interested, that's something that I'm very interested in working on. I'm doing some work on that. Plenty of space for doing research on that. And why does Nexus thing matter? To show the importance of Nexus, we can think of a thought experiment. I think Ali helped me to bring some of this thought experiment forward before reaching this point, but let's think together. How this whole crisis view would change if I told you, don't care about carbon. Forget about carbon and think about global water problem again. How would your response change?
No crisis.
No crisis, why?
I have 50 coal-fired power plants to produce electricity and do reverse osmosis all the way.
Yeah. If you relax carbon constraint, perfect. I will build low-cost, reliable, coal-based electricity production. I will build a lot of desalination everywhere, around the Mediterranean, around the Persian Gulf, Africa, etc. I will produce as much as water you want. And it's not that expensive anymore, especially using coal, which is an abundant resource. So that's why we did the system view. If you take one of the pins out, the constraint optimization goes away. It's not an optimization problem anymore. But the point is that we need to solve that global water crisis, accepting certain budgets of other issues that we have. So one is, we have a big carbon budget on our solution for water crisis. One constraint. Now think the other way. How the view of energy security would change if I ignore water crisis? Now let's look at the other side.
Same thing.
Same thing, but now I'm relaxing water constraints.
Yeah, because, thermal power plants need water for cooling, so...
That's one part of it. But then you still have the carbon constraint on them. But yes, part of it. Exactly. What else can I get if I have plenty of water?
Hydro.
Hydro, if I had real hydro dams, yes. But more than that, something easily producible in the US. Think of Iowa.
Nuclear energy?
Nuclear, yes, but more than that, biofuels. Right? If I didn't have the water crisis, I can plant a lot of corn and produce a lot of water, a lot of ethanol. No need to import gasoline.
Not that straightforward, because you need other resources, not just water to plant crops.
Yeah, but those are not in the short, fertilizers, etc. You have those.
And land. You have the land limitation.
You have land limitation, but if you had water, you have a lot of arable land which we are not cultivating now. If you had water, you could take them under cultivation, basically. What, of course, there will be other resources kicking in, but the first constraint which is binding here is water for biofuels production. And then if we ignore food security requirements, I think your point, then I can convert all soybeans and corn and wheat into biofuels, and I will get rid of the energy problem and part of the carbon problem. You see, so I have this multi-dimensional constraint optimization. Whenever I want to increase one, the other problem kicks in. That's why I need to think with a system view and see all these constraints together. Now let me give more numbers. So let's see why the nexus of these three and not other factors. So food sector is one of the largest consumers of energy globally. 30% of energy goes to food. Water, nice discussions we had, is a key input to lots of subsectors of the energy sector. You need water for cooling of thermal power plants, power plants, nuclear, you need water for production of biofuels, etc. And then when you work on this global energy system, you see a trade-off on water issue. You can go with very water-intensive solutions like nuclear, which have very low carbon footprint, or you can go with more carbon-intensive, less water-intensive solutions. So still you get this constraint on the Pareto frontier between water and carbon budget. Energy, as we discussed, is a major input to water supply, so I can build desalination. I'm working with a group in Texas State University. We are building a facility for air to water. The idea is that you have a lot of places which have humid air, but they don't have fresh water resources. So we are building a greenhouse there, which you use, cooling system to convert the evaporation, the humidity in the air into drips of water in a closed system and produce agricultural products. So if you had plenty of energy, free energy, I would go to all these deserts, build these greenhouses and start producing food in places which are traditionally not food producers. If I had enough energy, I could transport water from areas that is not being used to areas with high demand. So at the end, a lot of those constraints on water are boiling into how much energy I'm going to use. We discussed this, agriculture is an input to energy. Then here we have a lot of nice stories. And access to energy is a driver of global water crisis. The prime example is India, and also countries like India. So the whole problem that I talked about, about depletion of groundwater, this is a phenomenon of the recent 2 to 3 past decades. We didn't have this problem in the past. Why? Because the wells were not electrified. They were using conventional technologies. Conventional technologies were expensive, so you had to limit how much you could go down. Electrification of irrigation systems reduced the marginal cost of access to water significantly, so increased the incentive for intensive use of water, depletion of water resources. There is a very nice example here, that's perfect. So they come up with the idea, they say, solar energy, renewable is very important, etc. In India, they went and installed a lot of solar panels on pumps on water wells. Okay, fine. You see two major backfiring effects here. Let me ask you, what do you think? Why solar panel, nice renewable energy would intensify water crisis in quadratic way, I would say? Any guesses?
Can only happen in my state, farmers don't have to pay even a penny for
That's one
electricity.
thing. It makes the marginal cost of extracting water zero, absolutely zero. You put a fixed cost, but the marginal cost is zero. You're not paying anything for fuel. So you go to the corner solution of let me extract as much as possible. With electricity, at least you have to pay something for the electricity, so you can control the use by charging the electricity bill. That's one effect. Another effect comes from nature. What's the best time to irrigate a field in terms of the time of the day? What's
Nice.
nights, because the evaporation is minimal. It's cooler, you don't have the sun. But can you run a solar-based pump at midnight?
Unless you have a battery.
Unless you have a battery, it's very expensive. When is the maximum efficiency of solar panels? Midday. So you have to run them midday, but midday is the worst time for irrigation because you lose a lot of water for evaporation. That's another thing. If you don't think of the systemic interactions carefully, you may get backfire forces. Then the carbon footprint of agricultural water. So a lot of active research on that. I explained, you get the wells deeper and deeper, but then when you extract water from a well deep 200 meters below the earth, you have to consume electricity for that, but that electricity has carbon footprints. So getting more water exponentially increases the physics laws, right? Exponentially increases the carbon footprint for the agriculture sector. Then you get the water and carbon footprint of food waste, that's the water you lose in the food waste chain, and the agriculture has water resources. So I just put examples. You can go with 10 more slides if I had time, all those nitty-gritty of interactions in the system, but I think you've got an idea of why we need to think in terms of it. Nexus approach. Now I put together all the solutions which exist for water crisis. And that's my classification. I said, if I want to close this gap, what are my major intervention areas? Here I can say, okay, let me first ask the global citizens to reduce the per capita water footprint. Encourage people to consume less water. One would be, take more efficient shower, etc., which quantitatively really doesn't matter in this picture. It's a tiny, tiny effect. But there are other things. One is the diet change, which can bring in a lot of saving. And as I said, countries have started this. I can reduce waste in the food chain. There are estimates that between 10 to 15% of water is just being lost due to the food waste, which you could have saved. Increasing energy efficiency will save you a lot of water. And migration, that's a last resort, but sometimes it's inevitable. Migration from hot, less water abundant areas to more milder areas still saves water. Because now you don't need to run highly water energy intensive AC units during the summer or during the winter, etc. So that's one type of solutions at the demand side. That's a demand-driven solution. Now you can look at also the supply side solutions. So one obvious thing which people do is looking into new aquifers, like looking into deep ocean water resources, all these unconventional things that we did with oil, discovery of shale oil. Now they're looking for similar ones for water. Not much success, but there are theoretical possibilities. Then rely on multiple use or recycling. I did a back of envelope calculation. This can save us between 5 to 10%, at maximum 5 to 10% of. It can bring in 5% of the water use because you cannot install reuse on the whole water use. Basically you lose all the rain-fed irrigation water. There is no recycling. Recycling can only be attached to industrial and domestic use, which is a smaller fraction. Desalination is a solution, but it still has its own limitations, many limitations, location limitations, environmental impacts, and energy use. And then unconventional, new innovative solutions like atmosphere to water, etc. What are the problems with most of them? Carbon budgets. As I said, if you relax carbon, they will work, but all of them, if you look at them, they are carbon intensive. Unless you find innovative solutions to make it zero carbon. Like you use recycling, help me, a colleague working on algae. So you make recycling in a way that you put energy there, generate algae, convert algae into an advanced generation biofuels technology into ethanol and sort of make it a zero carbon budget. But it requires a lot of innovation. So that's the other side, when you rely on producing more water. And then in between, you have the improvement of efficiency and improvement of productivity. Improvement of efficiency, I mean getting water to the root of the plant. Increasing productivity is after that point, basically. So one is more physical, the other is more biological factor. So improved irrigation technologies, people have used sprinkle and other renew technologies. Rely more on rain-fed agriculture. All those new technologies for smart agriculture, generate water markets to encourage the trade of water between high-value users and low-value users. That's one part. And then increase productivity. Like move the production to more efficient locations, use GMOs, and then on other technologies like cellular to energy conversion. So that's the whole portfolio of solutions we have. I don't think I have dropped any. 5 minutes? Yeah, I will finish.
Quickly, a quick question. Would the nuclear power resolve a part of that supply side problems? But then we don't have any carbon.
So if I put nuclear here, I don't have carbon, but nuclear has its own problems of waste, right? Waste and environmental risk in the case of, explosion, etc. So it's a very, since I have worked in energy, it's one of the most controversial issues. I think we brought it even last year when we had this panel about water or climate. That's a very controversial solution because from water footprint perspective, from carbon footprint perspective, it's a perfect thing. Zero carbon or near zero, reliable, cheap, etc. Then you have all these environmental issues.
The other issue that kicks in there is the issue of global warming. At the end of the day, a nuclear power plant is a thermal power plant that needs water for cooling. Cold water for cooling. 2 years ago, France, that produced 90% of the electricity by nuclear power, had to shut it down because the water that they used for cooling was too
was
hot,
not cool
and they
enough.
had to import from England electricity. So it may not be a solution, it may be a catch-22.
Thank you. I learned this from you.
Supporting this point, it was my master's thesis which talked about the same thing, that what is the effect of climate change on thermal power plants. So the statistics say that if there is a 0.1 degree Celsius increase in the temperature, there's a significant drop in the efficiency of the thermal power plant specifically.
Yeah. And also, you also get the same effect for solars, etc. I think in the next version I should add one slide for the effect of climate change. These are important points I missed. Thank you. Okay, so the bottom line I put together in my model was none of the solutions would deliver you more than maybe 5-6% of the gap that you have in mind. So you don't have any corner solution basically. None of them is individual ultimate solution. You have to have a portfolio of solutions and also a lot of variety in local variations. And the budget constraints, we talked about carbon budget. On top of that, we have another thing, which is, I think, Deep's area's expertise. I was expecting him to guide us on that, nitrogen budget. I can increase productivity of agriculture, but for every unit of agriculture productivity improvement, I have to put more fertilizer, but my budget for N is also, so I have a budget for C and a budget for N. These two, and of course for O2. So I cannot rely on too much improved productivity in agriculture. I have to solve the whole solutions under this constraint. What are other limitations and challenges that these solutions still are not certain? So one is that they interact a lot with other factors. I think we covered that. There are a lot of unintended and unknown consequences of this technology that I'm talking. Like GMO is one big prime example. It's nice for increasing productivity, but lots of controversies around it. Water efficient technologies are Springer. They are good, but then we know all this rebound effect that I told the story. Another thing is that water has zero economics. Because water has a very low value per volume, you don't have, for oil, you have oil, futures contracts, markets, traders, investment banks. Water, you don't have it. Water is a very low value commodity. That's why the whole economic incentives, which are guiding us in other markets, are not working for water yet. That's another constraint we have. We have a lot of behavioral factors in water, like adoption of efficient irrigation technology. You see a lot of resistance because there are lots of social factors coming there. Huge investment is needed to realize this. It's easy to say, but then at the global level, you have competition for capital, for transforming energy system, for expanding healthcare, education, etc. Water is only one of those global issues. And so you need a lot of capital to realize that, and there's a lot of political barriers because I think you're convinced this is a long-term problem, no short-term thing, but politicians, they come with the cycles of elections, etc. So it's short-termism versus long-term solutions. So these are limitations. Each needs a lot of studies on that. So let me conclude by that. Time is also over. So there is a lot of need for large-scale global modeling of water. Compared to other fields like energy, we are very behind. For energy, we very well understand what's the exact capacity of renewable in each region, what happens if I shut down, one nuclear power plant in Japan because of earthquake. We see it immediately on the system. We don't have it for water yet, so we have a long way of building these models, embedding agriculture, water, etc. into a connected global system. There are modeling challenges basically because, as you see, the issue is a sum of local and global factors interacting with each other. A lot of uncertainty around performance of technology, the precipitation rate, temperature, climate change, a lot of economics uncertainty and human behavior uncertainty. But I think that's also opportunity for us. For scientists who want to collaborate on that, I think it's an area that is rising and one can do a lot of work by combining engineering and economics optimization knowledge into the systems. So let me conclude here. Thank you very much for hosting me, and if you're interested in doing research in this area,